Hello. In this video we are going to estimate the energy yielding of our photovoltaic plant. First of all, here we can see the typical values in this table of the different losses that we can find in photovoltaic plants. Due to dirtiness, we can find values between 0 for a very clean installation or until 8% if the dirtiness is really high over our modules. About the inverter losses attending to the technology of the inverter, we can expect losses between 3 to 10% attending to the technology, if it includes transformer, the quality of the inverter that we are using in our plant. Mismatching losses can vary between 2 to 5%. If you are using bad modules with a bad quality, this value can increase until 8% in some cases. Wiring losses can be established to values between 1 to 2% attending to the design of the wires that we can do. We can improve the cross-section of the wires and reduce this value if we want. About reflection losses, typical values are around 2%, but in some cases with a bad quality modules that are using some anti-reflexive layers that are not really good, we can arrive to values of 6% in this type of situation. The transformer, if we are using out of the inverter a transformer in order to adjust the levels of voltages to the power grid, to the power network, we have to include the losses that can vary between 1 to 5%. But if the transformer is included in the same inverter, we have the losses in the transformer included in the losses of the inverter, as is going to happen in our case. About availability losses, we can find values between 1 to 5% attending to the contract of maintenance that we have for our plant or attending to the case that we give to the photovoltaic plant. If we are seeing continuously if the plant is working well, we can expect losses that are going to be in the order of 1 to 2%. And due to the tolerance of the modules, we can consider variations between plus minus 2% to 10%. We are going to work always with values, with negative values, in order to find a smaller power than the one included in the levels of the modules. The values that we are using in the next pages are included in the following tables. As you can see, we are using tilt and orientation losses of 0% because we are going to use the peak sun hours that corresponds to the characteristics of our plant. So in this case, we have to consider 0% for this factor. Also, we are not including shading in the photovoltaic field. The dirtiness losses is a common value of 2%. Mismatching losses due to the module is really good and is a well-known manufacturer. We expect to have values in the order of 2%. Just the same for the reflection losses. And about the wiring losses, we have calculated in a previous video, and we have established that the factor of losses due to wiring is around 0.77%. The inverter losses using the European efficiency of the inverter are 7%. So the inverter is going to have an efficiency of 93%. The transformer losses are nil because are included in the losses of the inverter. About availability losses, we are using 1%, and we are including also the tolerance of the module in the negative part. We are thinking that we are going to have a little less of power than the rated power for the module. So we are including the minimum value of the tolerance, the negative one, and all these factors appears in the calculation of the performance ratio of this installation. All these values are fixed and corresponds to this part of the equation that we are going to use to evaluate the energy yielding of the plant. And the one that we are going to calculate for each month is the performance ratio for the temperature. In the next slide, you are going to see the peak sun hours expected for each month from January, that has 3.2 peak sun hours, to December with 2.8, and in summer we have maximum values in July of 6.19 peak sun hours. About the temperatures, we can see the variation of temperatures between winter with minimum values near to 12 Celsius degrees to the highest temperatures, average values that we can expect in August. During some days in August, we can reach maximum values near to 40 degrees in Valencia. But here, we are using the average value of a day in August, of an average day in August. With these values, we can calculate the losses due to the temperature using this expression, in which we have to calculate the cell temperature for the operating conditions that we are establishing, and we will need also the temperature coefficient of the power for this model. The cell temperature is calculated here. We are going to use the ambient temperature that we have in this table, and we are going to need also the normal operating cell temperature that is included in the datasheet of the manufacturers. Usually for crystalline models, this value is around 47 Celsius degrees, and in order to calculate the cell temperature, remember that we are going to use the standard test conditions. So here in the radians, we are using the value that corresponds to standard test conditions. Remember that the energy produced by the photovoltaic plant is going to be equal to the peak sun hours multiplied by the photovoltaic power multiplied by the performance ratio. Peak sun hours and photovoltaic power are calculated or measured for 1000 watts per square meter. So also the performance ratio of the temperature must be calculated for the same conditions. With these expressions, here you have the expression that allows us to calculate the temperature coefficient of the power if the value is not included in the datasheet. And with all this expression, we can obtain the values included in this table. Here we have the ambient temperature for all the months of the year and the average value for all the year in Valencia. Here we have calculated, using the previous expression, the temperature of the modules, the expected temperature of the modules, and the average value. You can see that in summer the temperatures are going to be higher than 60 Celsius degrees. Using the previous expressions, we are calculating the losses due to temperatures and also the performance ratio due to the temperature. With these factors, we can see that the losses in summer are higher than in winter. And due to that, the overall performance ratio of the installation that includes this factor, the performance ratio for the temperature, and the rest of factors, distance, reflections, inverters, wiring, and others, if we multiply all together, we obtain the performance ratio for each of the months. And we can see that in summer the value is smaller than in winter due to the effect of the temperature. Using average values, we can do some calculations, as we are going to see in next slides. The performance ratio, the average performance ratio for a plant is going to be in the order of 0.76. That is a value that is accepted in photovoltaic installations as a common value that we can really find in a real installation. Here we have the calculation of the energy yielding for different intervals of times. We have the different months of the year, we have the number of days of each of the months, and the peak sun hours that we have obtained from a website, just like the one that we are using, the PVHs. And here is the performance ratio that we have calculated in the previous slide, considering all the factors. Remember that the variation in these values is due to the power factor, the performance ratio of the temperature. With this value multiplying by the photovoltaic field that is constant for all the months, we can obtain the energy production per day, per week, or per month using the different values. We have to multiply this value by 7 in order to obtain the values per week, and multiplying this value by 31, we are going to obtain the monthly production. The average values for a photovoltaic plant in Valencia says that we can expect around 4.78 peaks and hours as an average value in an average day of the year. The performance ratio average value is 0.76, and the whole production for this plant is in the order of 80 megawatts hours. That can be calculated using the average value per day and multiplying by the number of days in the year. In the next slide, we have a summary of the most important magnitudes or characteristics of this installation. The peaks and hours that we can expect in Valencia is 1,746. The yearly production is here, near 80 megawatts hours, and the expected production per kilowatt peak of our installation, and then with this value we can compare with other installations that are near to the one that we are designing, is 1,330. This is the value of kilowatts hour per kilowatt peak in our installation. This is the expected production, the expected energy produced by the plant in the first year. But after some years, due to degradation of the modules, we are going to have a reduction in the energy produced by our photovoltaic plant. So the first year we are going to have this production, and we are considering losses of 0.5% every year due to the degradation, due to the aging of the modules. So you can see how the production is reduced along the time until we arrive to values that are near 70 megawatts respect to the previous values that are around 80 megawatts hour. So we have to consider these effects in order to calculate correctly the incomes, the economic incomes that are going to produce this type of photovoltaic plants. Here you have some calculations about the annual yielding of energy using the average values, the average performance ratio 0.76, the peaks and hours per day in an average day multiplied by the number of days in a year, and the peak power of our installation in kilowatts. So this is the value of the energy yielding in a year, and the same can be done for a specific month. Here we have done for January as an example. This is the performance ratio for January, the peaks and hours average value for a day of January, the number of days, and the photovoltaic plant peak power. And here is the production expected for an average month of January. You can use several programs that you are going to find in the webs about the calculation in photovoltaic plants, the yielding of photovoltaic plants. And here, for example, is one that is in Spanish that you are going to find the equivalents in English in the website. The production is quite similar to the one that we are calculating, and you can see that the values are really equivalent to the ones that we are using with a different source of peaks and hours, because here the peaks and hours are a little different than the ones that we are using. In the next slide, we are including the different signals that we can find in the monitor systems. We are going to have information about the input voltages and current in the DC part. We are also having information about the power produced by the photovoltaic field. Also, we are going to have information about the voltage and the current in the AC section, and the AC power produced by the inverter, active power, that is represented, remember, by letter P, because in some cases also we are going to have information about the reactive power in the output of the inverter, that is represented by this other letter. Also, if we want to know if the installation is working correctly, we will need to include the measurement of the irradiance in the same plane than the photovoltaic modules. In order to calculate from this value, we can calculate the peaks and hours that really are arriving to our modules, and then we are going to calculate the performance ratio that we have in our plant with real values in the operating conditions of the plant. Also, the ambient temperature is really an interesting parameter. Remember that we have to do this measurement under the shade. Usually we are going to install it in the back side of the modules, but with some distance respect to the modules in order to avoid the heating that can produce the module in the sensor. Also, it's interesting to measure the photovoltaic module temperature. So we are going to fix a sensor of temperature. Usually there are resistances that are sensible to the temperature, and this measurement is acquired by the monitor system in order to have all the variables that we can include in the calculation of the performance reality of our plant. The reactive power, and finally the energy production, the number of working hours in our plant, and other parameters that can be interesting from the point of view of the monitor system. About the alarm signals, here you have a list of the most common alarm signals or warning that we are going to find in monitor systems, if the system is working correctly or there is some disconnection, if the temperature is high and then the system is disconnected. So there are several information that can be interesting to the operator of the system. If the inverter is working with high temperatures, the inverter or the DC-DC converter, if the grid is stable. So, well, there are a lot of signals that we can monitor in order to determine if we have some failures. We have to detect where is the problem, if it's in the DC side, in the grid, the inverter. About the maintenance in this type of plants, we can have 1 or 2 visits to the plant in order to revise if it's working correctly. We can see if we have some problems in the wires, in the modules, in the photovoltaic plant, or in the panels, in the electrical panels. And also we can use thermography in order to verify that the modules, wires, protection circuits, inverters are working correctly with a stable temperature in the limits of operation of this type of systems. We can measure and verify also voltages and currents in the different parts of the sections, AC and DC sides, in the modules, in the strings, after grouping, after connecting in parallel several strings. So we will need multimeters in order to verify voltages and currents. And also we have to verify the protection device, if the inverter is working correctly, and also it's interesting to revise once every year at least the terminals, if they are correctly mounted and well connected, and also if the wires are in good state. And this is the last slide about the energy yielding estimation. Many thanks.